All right. Everybody see the slide?
Yes.
Okay. Shay?
Yeah, I see it.
Okay. So we'll talk a little bit about electric and magnetic fields. This is, and I'm not going to go into Maxwell's equations. This was the dreaded course in college. Nobody wanted to take fields and waves.
Oh, darn.
So we'll talk a little bit about electric fields and capacitors because they make use of electric fields and how they behave. Magnetic fields and inductors use magnetic fields. And then we'll talk a little bit about series and parallel circuits and Kirchhoff's laws. So an electric field, which you call an E field, is created when there's a potential difference between two conductors. A magnetic field, which we call a B field, I'm not sure why we use B because I think we measure it in Orsted's or something, but anyway. You get a magnetic field when there's a flow of charge or current flow due to a potential difference. These two fields can normally, they're both there at the same time, and there's current flowing, but they're orthogonal. In other words, they're 90 degrees relative to one another. So when we produce an electromagnetic wave, it's called electromagnetic because it consists of an E field and a B field, or electric field and a magnetic field. One is going the E field is kind of be translated along the conductor the way the current is flowing, where the magnetic field or the B field is orthogonal to it and tends to be circular around the current flow. It's kind of like this little diagram over here, and I never figured out where the white box came from, and I never could get rid of it. So it's nothing important, and I don't know why it's there. These are just some different examples of electric fields. So if we have just single pointed electrodes that have potential difference between them, you can see that the E field radiates from one out in a radial pattern. It is in the opposite direction and flows in to the other polarity. If we have the same polarity on those two electrodes, then those E fields are going to oppose one another. So you see that distorted pattern. And whether it's negative or positive, the blue is a positive charge and the red is negative charge. I would have used the other colors, but I didn't do it. So like charges repel one another or oppose one another. In the case of the top right, okay, we have opposing charges, so they attract one another, and there's a force between them that's going to be the opposite of the force between the like polarities. In one case, it's a force trying to push them apart. In the other case, there's a force trying to pull them together. They used to demonstrate this with a little thing called electroscope, which was a little glass jar, that had a rod with a couple pieces of gold leaf on it. And if you charged it up with static electricity, because the two gold leaves had the same charge, that you actually physically move apart. They had a way to take the charge off of one of them, and then they'd come back together. So it was a good demonstration. It's kind of hard for me to do here. These lower ones are showing where you've got like a point charge and some sort of a plane or plate. So you're going to have that field between the two as long as they're opposite charges. In the case of two planes, and this is where capacitors come in, we have that field pretty much confined between the two plates. You don't see much charge going around the sides. In the bottom right is essentially what happens in a piece of coax, where you have a center conductor surrounded by some sort of what we call dielectric or insulator, and then a tubular conductor. It's usually some form of like copper braid. It could actually be solid copper in the case of what we call hardline. And you see that the field is contained, like in the capacitor, between the center conductor and the outer conductor. And you have that field either in or out, depending on the polarity. This is just things showing the kind of the field strength. It's proportional to the area of the plates and the distance between them. And that equates essentially to the amount of capacitance, which is how much energy can be stored. The stronger that E field is, the more energy you can store. So the closer the plates are, or the larger the area, the more energy it will store. This is just showing how the charges line up in a capacitor. And we have the electric field between the positive charged element and the negative charged element, where we've got free electrons down here on the blue side, and in essence, holes or atoms that are missing electrons all lined up on this side. The other interesting thing is there's a thing called skin effect. Because like charges repel, I've got that plate full of like charges. They try to separate from one another as far as they can. So that tends to push them to the surface. And you'll actually see that on wire. The free electrons, or the charges, oppose one another, and they tend to migrate to the outer side, the outside of the conductor, not the inside. And the more potential there is, or the higher the voltage, the more you see that effect. You see it on very high voltage transmission lines, and they'll either use a bunch of parallel lines, so they have more surface area, or they're actually using maybe iron or aluminum with a copper coating on it, because the current is all going to be on the skin or the outside. Okay, so capacitors, or how we make use of electric fields. and they store energy in the electric field that's in between those charged plates. We call or we measure capacitance in farads, named after Michael Faraday, who sort of discovered the effect. So the definition is that a 1 farad capacitor, which is a very, very large capacitor, can store 1 coulomb of charge at 1 volt. And you don't have to remember that a coulomb is 6.25 times 10 to the 18th, or 6.25 billion charges, elementary charges, equivalent to free electrons. And that, if you remember, an amp was 1 coulomb per second. So a 1 farad capacitor can hold 1 amp second of charge at 1 volt. Physically, it's essentially 2 metal plates for most simple capacitors. It may be more than 2. They may actually stack them, but they're separated by some what we call dielectric or insulator. And like I said, the closer the plates are, the more capacitance, the stronger the field, so the more energy you can store. But obviously, the closer they are, the less voltage it would take to bridge that dielectric. So a high voltage capacitor is going to be physically large with a large or thick dielectric, whereas very low voltage, like 5-volt things, can be made very small. One of the first examples was called a Leyden jar. I think it was named after some guy called Leyden, which was just a jar that had a some sort of metal wrapper on the outside and one on the inside in a way to make contact with the two. And the glass jar itself was the dielectric. And you could actually charge that up and it would hold the charge, glass being a very good dielectric, low loss. Benjamin Franklin was around in that time, who's responsible for the names of a lot of these things, and he got some of them wrong. He created what was called the Franklin square, which is just 2 plates separated by a piece of glass. It was a lot easier to construct. And that's kind of the basis for a lot of today's capacitors, where instead of just being flat plates, we tend to roll them up and make them tubular. Here's some examples of current capacitors. You'll see some, what we call these are like trimmers or air variable capacitors. And one of these sets of plates rotates so they mesh with one another. And depending on the overlap, will determine the amount of capacitance. These kind of orangey brown things are probably the most common. They're ceramic. It's a piece of ceramic with a metal plating on both sides, and the wires connect to it. So it's a very simple, called a disc capacitor. A lot of these others are electrolytics, which is slightly different. And there's an electrolyte in there, and it relies on a chemical process, allows you to store more energy in it than you would in a straight non-electrolytic capacitor. So you can get very high capacitance for electrolytics. The downside is they're polarized. In other words, they'll only work properly in one direction. If you put a high reverse voltage on them, they'll go up like a firecracker. You have some others down here, like this, I think is probably a Mylar, which is the dielectric and the like foil all wrapped up in that little package. There's the typical ceramic disc capacitor and how they're constructed. Like I said, it's just a plating, metal plating on the outside, and then they put some conformal coating on it. This is a kind of one of the electrolytics. This would be a tantalum, where there's some electrolyte in there. It's somewhat similar to a battery, actually. Okay, so we talked about capacitors storing a charge or storing energy in the electrostatic field. So what does that look like? And I set up this little circuit with a series resistor to limit the current and a 1 microfarad capacitor. We tend to use that little mu or micro sign to indicate that it's a millionth of a farad. And we're putting a 10 hertz square wave on it. So if we plot what that looks like, the blue up here is our voltage square wave. It's going up to 10 volts, and it lasts for a tenth of a second, or actually half of that. The yellow is the actual voltage across the capacitor. So we see that when we first apply the voltage from the source, the capacitor is at 0 volts. It slowly charges up until it finally gets up to 10 volts. At that point, we took the voltage away and we see the charge dissipate back. So we're going to have current flow in the opposite direction. And that's what we see on the second plot is the actual current going through the circuit or the capacitor, because the current's going to be the same through both the resistor and the capacitor. So there's initially a very high current, and it's only limited by that resistor. And as the capacitor charges up, okay, the difference in voltage between the two is less. So the current dissipates to 0. So when the capacitor is fully charged, there's no more current flowing into it. When we stop charging it or take the voltage away, then it starts to discharge. So we have an immediate negative current coming out of it that then dissipates back to 0. So you can see just from this, and this is only 10 hertz, that the frequency is going to have an effect on how this capacitor operates. And we'll talk about that in a later session when we get into reactance and impedance. So capacitance is the ability to store energy in an electric field. Pretty sure that's a test question. We measure it in farads. We typically construct them of plates separated by an insulator or dielectric. The current decreases as the capacitor charges up to whatever the applied voltage is. And we say that the current leads the voltage. Because you saw on that plot, initially the voltage was 0, but the current was maximum. So that brings us to this saying that a lot of people use to remember this stuff. Eli the Iceman. So we say that E, or the voltage for L, an inductor, leads the current. Likewise, I, the current in a capacitor, leads the voltage E. Does that one make sense?
Marginally, I think it's going to take some study, Robert.
Okay, just remember that in the capacitor, okay, it appears to be essentially zero resistance. So you get a high current. And the more it charges, the less current you got. So that's why we say the current leads the voltage.
Could you say that again?
Okay. When we apply a voltage to the capacitor, it initially appears, if it's not charged up, to be 0 ohms, 0 resistance. So we're going to get a maximum current flow initially. As the charge builds up, the more energy we store in that field, the voltage is building up and the current is therefore decreasing because it's a function of the difference between the applied voltage and the voltage across the plates of the capacitor. So the more it charges up, the less potential difference there is, so there's less current flow. At what we call 5 time constants, it's going to be at 95%. And we'll talk about time constants later too. So when we are going to talk about inductors next, and it's a very similar phenomenon, but the opposite.
Oh, good.
Well, it might help you understand the other one. So we have magnetic fields that are created when we have current flowing. So that creates a magnetic field orthogonal to the current flow. And it's usually used like the right-hand rule. So if you point your thumb in the direction of current flow, the way your fingers curl is the direction of the magnetic lines of force that are going to be around it. And, it's like if you ever played with magnets, it's just like electric fields, magnetic fields, like polarities oppose one another, opposite polarities attract one another. Works the same way. So down at the bottom, when we show current flowing through those wires, and we see that magnetic field surrounding it, and the direction of flow of that magnetic field is a function of which way the current's going. Now, if we take that wire and we kind of wrap it into a coil, we can cause those magnetic lines of force or field lines to, I guess, coalesce into the center of that coil. So they get concentrated in the middle. And if you were to try to follow around that coil with the right-hand rule there, you'd see that they add in the middle and not on the outside. So most of the electromagnetic field is going to be combined within that coil. The thing over there on the bottom right is just showing the Earth's magnetic field. Since we're just a big magnet. This is a little clearer, I guess, of a coil showing the magnetic lines of force being concentrated through the center of that coil of wire. with the current flowing through it. So as the current flows through it, it starts building up a magnetic field similar to when we charged up the capacitor. Except in this case, we're storing energy in the magnetic field as opposed to the electrostatic field. So as long as there's current flowing through this inductor, there's going to be a magnetic field. And how much energy is stored is going to be a function of the amount of current and the inductance of that coil, which is kind of the number of turns and what the diameter of the coil is, several factors, and the permeability of equivalent to the dielectric and the capacitor. What's in the center of this coil gives it its permeability. And in this case, it would just be air, which has a specific factor. If we add something, I don't have it there yet. Okay. Like a piece of iron or ferrite that has a much higher permeability than air, it's going to give it a much higher inductance and allow it to store more energy, more magnetic energy in that magnetic field. This is showing the amount of energy that's actually stored in the inductor, and it's the kind of greenish area under the curve. So when we first apply a voltage to the inductor, we have I should say, unlike the capacitor, which appeared to be 0 ohms initially, the inductor is going to appear to be infinite ohms. So whatever voltage we apply to it initially is what the voltage across the inductor is going to be. The current, therefore, is going to start off at 0, where in the capacitor, the current started at whatever the maximum was, limited by that series resistor. So you can see it kind of works just the opposite. And as the current increases through that inductor, the voltage decreases. So once again, after 5 time constants, the voltage across the inductor is going to be essentially 0 or less than 5%. And the current through it is going to be whatever the maximum current limit is, depending on the amount of voltage and the resistance in series with it. So the area under that curve is actually the equivalent to the amount of energy that's stored in joules in that inductor. And the formula for that is the energy in joules is 1/2 times the inductance times the current squared. That one you don't have to remember. These are some typical inductors. Over here on the top left, we have what's called a toroid. And these are usually ferrite material in the shape of a donut. In some cases, it could be iron oxide. Its material has very high permeability, so we get a lot of inductance per turn. And the other thing is it confines the magnetic field entirely within this donut. So you don't have interaction. If you had 2 of these next to one another, There'd be very little interaction between them because the magnetic field is contained. Whereas in this linear one, most of the field in the middle is contained, but out on the ends, I've got some, so you'd have to be careful what it's next to. It's a little bit directional. These bottom two are some surface mount inductors. They're not to scale. These are actually fairly small things, probably less than maybe between 1/8 of an inch and 1/4 inch square. We sometimes see inductors looking like a resistor package. It has a similar coating, color coding. It's not the same, but it works about the same way. These are what we usually call chokes, and it's a small inductance. It might be 30 microhenries or something like that. Usually you use them in series with power supply inputs to devices to help filter out some of the noise. This is just another sort of a surface mount inductor. Okay, I did a similar circuit with a limiting resistor and a 10 millihenry inductor. And you can see that the applied voltage, okay, and the current or the voltage across the inductor are almost the same at the beginning. The voltage drops across the inductor as the current increases through the inductor. Likewise, when we take that voltage away, we get a negative voltage spike, which decreases, and the current through it decreases exponentially. So this is the case where we say Eli, in other words, the voltage in the inductor L leads the current. The voltage is high, the current is 0. So the voltage goes up before the current goes up. That's why we say it leads. Whereas in the capacitor, the current leads the voltage. Did that help any?
Yeah, it was good. It's complicated. I think it's going to take some study.
Okay.
I like
So,
the Iceman. I'm trying to figure out what that means, Robert.
okay.
Can you go through the Eli the Iceman thing? Because I was thinking about it while you were talking.
Okay. Eli the Iceman. So E, okay, stands for voltage. L stands for inductor. I stands for current. So Eli means that the voltage in an inductor leads the current. In other words, the voltage increases before the current increases. In the capacitor or the Iceman, the current in the capacitor leads the voltage. Okay, so the current increases before the voltage increases.
And that, I mean, that's so it would seem like that's instantaneous, but I guess it's not. I'm trying to figure out why do we need to know that?
Well,
Other than it's part of basic physics of components.
yeah, and it's uh, part of reactance and phase shift. Because what you're seeing is a 90-degree phase difference between the voltage and the current in an inductor and a capacitor.
Oh, okay, I got it.
And depending on, and when you look at that circuit, when there's a resistor in there, okay, then the phase shift is not totally 90 degrees. And yeah, that will come about later when we talk more about phase and reactance. So this is kind of to help you understand basically what's going on in an inductor and a capacitor. The key thing is they're storing magnetic energy and electrostatic energy. And we talk about resonance a little later, maybe next week, which is kind of fundamental to radio. You need to have a resonant circuit pretty much. And you do that by combining a capacitor and an inductor, either in series or parallel. So you're charging up the capacitor, and when it stops charging, current stops flowing. Okay, and it starts to discharge. That current going through, if it was in series, inductor is going to start charging the magnetic field in the inductor. So you're going to transfer that energy in the capacitor completely over to the inductor. The field in the inductor at some point is going to collapse and recharge the capacitor. So you're going to have that energy moving back and forth between the inductor and the capacitor. And if there's no loss, it would sit there and oscillate forever. And if the values for the inductor and the capacitor for a given frequency make them have equal reactances, in other words, storing the same amount of energy, both in the E field and the B field, it's going to sit there and oscillate in essence forever. And that's what you would call a resonant or a tuned circuit.
And
we
that's
make
how,
use of those. Go ahead.
so that's how you shift phase, by changing the capacitance and the inductance.
Well, that affects it, yes. Series resistance affects the phase. The frequency will affect the phase. When we talk about alternating current and higher frequencies, it gets much more complicated. But the key thing is that we're storing energy either in the electrostatic field in the capacitor or the magnetic field in the inductor. And I don't know if I mentioned it before, but we never lose energy. All we do is transform it. We can move it around from the inductor to the capacitor, or we can generate heat in a resistor, but the same amount of energy is still there in the universe. It's either heat, or it's E field, or it's B field, or it's something, but the total amount of energy never changes. All we do is move it around or transform it. Okay, so the other thing on inductors, we measure them in henries, named after some guy named Henry. Forgot his first name. Basically, they're constructed from coils of some sort of conductive wire, and that the current increases as the magnetic field increases. So initially, there's no current flow through the inductor, and over a a period of time, 5 time constants worth, we'll talk about a time constant later, that current will go to its maximum value. If it was a perfect inductor and had no resistance, then you can have an infinite current flowing through it. And you just remember that voltage leads the current, or Eli, as part of the Eli the Iceman.